To start us off, we're going to have Dr. Samantha Arundel, Senior Science Advisor on National Geospatial Program of U.S. Geological Survey, talking to us about an intelligent national map coordinating structured analysis and scientific validation across authoritative geospatial data. It's a mouthful just to say that. So we're looking forward to hearing her talking to us a little bit about the U.S. Geological Survey's national map, a foundation for critical data across the country. Dr. Samantha Arundel, welcome.
Hey, everybody. Thanks so much for having me here. I hope I can hear myself over the person behind me. I'm Sam Arundel. I'm a real live research scientist from the U.S. Geological Survey. I wasn't sure, I've never been to this conference, wasn't really sure who the audience would be, but here we are. I'm not used to speaking in this close to the microphone either, so you'll have to bear with me. Let's see. So I work for the United States Geological Survey, which is part of the Department of the Interior, which is part of the executive branch of the U.S. government. So I'm a civil servant. I also work for the National Geospatial Program, which is underneath the USGS, and we have a small research team called the Center of Excellence for Geospatial Information Science that I was a research scientist in. Now I direct that group. And I also act as a senior science advisor to the USGS. We have been working in CGIS in the realm of AI for 20 years. So I'm going to talk a little bit about some of the work that we've been doing and where we're headed. I also want to give you a little background on me and why I feel like I'm qualified to stand up here in front of you and talk about this stuff. But I won't make it long, I promise. That's boring. So I've been working in the geospatial sciences since 1987. So I've seen a lot of changes over the years. I have 3 degrees in geography. Yep, my parents were super impressed. And I was a professor of geography before I moved to the U.S. Geological Survey. At the USGS, we have the best mission, I think, of all, which is science for a changing world. So you can think of the USGS as sort of the Earth science agency, kind of like how NASA is the space science agency. Because we're a science agency, we don't make policy, but we do inform it with our gold standard research, which is very important. So before I get started talking about our vision of an intelligent national map, I do want to look at the survey results. So I'm going to go ahead and send those out to everyone. And I did glance at them earlier. Let me make sure I can get this going, because I think it's really interesting. Let's see if I can get it to work. That's interesting. All right. So I'm sharing the poll results. I wish I could see them up here. Oh, I guess I can't share them to the group. That's odd. Okay. So you'll have to take my word for it. So the question was, when did AI research begin? And of course, the answer to that is based on how you define AI and how you define research. But the answers that we got range from 1941 to 2024. I got 108 responses for when AI research began. And I think this is interesting because it shows us an interesting phenomena which is that context matters, right? So where we are in the system, where we've been, what our life is, what sort of data and experiences we've been exposed to, the context really matters. So the answer is, we'll say the first time artificial intelligence was coined on paper in research in science was in 1955. So a lot of the answers were 1956, which I'm sure is related to that work, which was by John McCarthy at Dartmouth University. And I say 1955 because that's when he sent out his symposium invitation for a workshop called Artificial Intelligence that would follow the next year in 1956. But this idea of context I want you to keep in mind as we move forward. And also the idea that you get context from experience, but you can't always experience everything. And if you can't get the context from experience, you can use a good proxy, which is data. So artificial intelligence, like human intelligence, is only as strong as the data that supports it. Across industries, as we've seen here and around the world, industries are struggling with fragmented data, unvalidated data streams, inconsistent data. When we apply those data to AI, or we apply AI to those data, then what we get out the other end may look very powerful. So we might get results that look really great, they're flashy, shiny, but they're not reliable always. We want them to be trusted. So in the geospatial sciences, we offer a way forward, a clear example as to how we can change this pattern. By creating intelligent national maps, we can show how AI can be grounded, no pun intended, in reality, how it can be grounded in the truth with structured, validated data. So I'm going to say something that's really obvious. The volume of data is exploding. The volume of geospatial data has been exploding for decades. It's always been huge. We're the definition of big data. We get data from sensors, satellites, measurements in situ, constantly, that we have to integrate. And they're difficult to manage and integrate because they're geospatial data. And what do I mean by geospatial data? Those are data that have a connection to the real world. They have a connection to a location. That location, as far as we're concerned at the USGS, is pretty much on Earth, on our Earth or other planets. But national mapping is specifically interested in data for the nation. So we have these data, they're coming in all the time. They're fragmented, they're in different formats, they're siloed, quite often siloed. And when we use them, the outputs are often unreliable. It can be difficult just to get a hold of the data, to put the data together in workflows. And much of this is still done manually in the GIS realm. If we deploy or build AI systems on top of these kind of data, the output becomes reliable, unreliable, not reliable. Make sure you get that. So this is a challenge that many people face, not just in the geospatial industry, but you face this challenge in, say, finance, energy, environmental management, across the board. We find that more data doesn't necessarily mean good data, and it doesn't necessarily mean accurate results. We need a trusted structure for that. So we've been working on developing a trusted structure. And this is based on authoritative data. So at the USGS, we build, reference public data sets, such as elevation data for the country, hydrography for the country, that's mapping the boundaries of water features, which, as you know, change all the time. We map structures. We own the geographic names, which are the names that are used by all the federal entities. So, for example, Gulf of America. The important thing about these anchors is that, about these layers is they provide an anchor in reality, right? They're fundamental data. They've been validated. They provide an anchor. So you can think of them as sort of a calibration point around which you can tune your AI, tune your results, where your data are still consistent and trustworthy across applications. When I talk about an intelligent national map, I'm not talking about a specific app or a web browser. I'm really talking about an ecosystem of AI agents, and everybody here is tired of, I'm sure, of hearing about agents. But here's an application, so they're very important. In our intelligent national map, and here I just have a mock-up of what it might look like. Each agent has a specialty. So some agents might be extracting geographic features from imagery, like, for example, streams. Others might be validating that output against other data sets or against scientific literature. And still others might be producing features based on cartographic generalization principles so that they can be used at different scales. The agents, of course, don't run in isolation. They work together. And importantly, they're coordinated and they continuously are able to structure and validate data as information come in. The result of this, of course, is a system where the outputs are explainable, auditable, and, most important, trustworthy. There you go. Most AI systems take in raw and verified data and generate outputs without context. That may work for certain tasks, definitely. But if you need reliable data, if accuracy matters, then this can create risk. Risk is bad. An intelligent national map is different because the data are not left raw. They're processed, even if they're delivered raw, and they're processed automatically. The outputs aren't just predictions, they're explainable results that can be audited, that's very important, and used with confidence. So what do I mean by auditing? I mean, we can see exactly what happened. We can go back and determine where the data came from and what happened. For many industries represented here today, we believe the same principle applies, that you can improve your AI work and produce results that leaders can depend on by building it on validated data. It may be that that validation is part of the system itself. So think of the system as kind of like an assembly line. On one end, you have multiple inputs, GIS, right? We might have imagery, elevation, hydrography. And as we move along the pipeline, the agents align and standardize the data so that the different data sets can meet in the middle. This makes them constant across space, time, and sources. So that's how we are looking at managing the overwhelming data stream that we have coming at us all the time and turning it into AI-ready knowledge, because that's what we really want, is the knowledge that comes out in the end. We want the context to pass along, not just the data. This pipeline model is scalable in space and infrastructure. And it can be just as applicable outside of the geospatial realm. At least that's what we believe. So validation isn't just a step. It's not one step that happens at the end or it happens at the beginning. It should be a continuous loop and built into the system. What we're thinking about is having multiple peer review agents reviewing outputs, just like we do in the scientific world, where we wouldn't necessarily have a person reviewing, we would have an agent reviewing, and the agent could be looking from different perspectives, right? You could have a biologist reviewing your output, and you also might have a geologist. So an example is, say an agent produces a flood map from imagery. That output is checked before it's ever made public. And we can check it against the literature, against elevation data, against river networks. And if the flood outline doesn't seem to match, say, the terrain, then we can flag it in our immutable logs. So logs that can never be destroyed, because this is the federal government. And we can pass that back into the system. We can take it out, we can change the answer, and we can revalidate it. The purpose of this, again, is to ensure that the results are trustworthy. And this is really important in an age of fake news, or just information that we see so much information daily, it's really difficult to understand what's real. The most real thing we can do is base it on the physical world. It's also a way that we can bring in the rigor of scientific review into an AI workflow. So I'm going to give you a concrete example. During a flood event, time's really critical, right? Of course, an INM brings together all of these data, satellite images, river networks, whatever data are required, and within hours, not weeks, it can produce a validated flood extent map. That map, again, will already be checked against elevation, hydrography, other data sets, scientific literature. So it's not just a guess. It's consistent with what we know of the physical world. The value here is clear, of course. Insurers can assess the data, the claims faster, logistics companies can reroute work, governments, emergency management teams can decide where to place their resources best. Another example is wildfire. Inputs into wildfire might, here in this case, include aerial imagery and vegetation data, pretty simple, among maybe others. The AI agents identify the burn scars, then generalize those to different scales. So we have a local scale where you can see a very detailed burn perimeter, but then you can also take that information, generalize it, in other words, make it less precise, not less precise, just make it less busy, and put it into a national data set where you have other similar information from other burn scars that are collected to create a national data set. And that can be used for analysis of wildfire over bigger spaces and more time. You can see the use here, of course, outputs for this could be used by insurers measuring damage, utility companies managing risk, emergency responders, again, trying to figure out where to go to help when they're on the ground in the field. The key point here is the validation and the generalization, which is necessary for geographic features, are built into the workflow, making the data more accurate and usable. So I want to emphasize that this approach shouldn't be limited to mapping. Theoretically, it could apply to any industry that struggles with fragmented data. And I will tell you that geospatial data is a very difficult part. difficult arena to make this happen. So if we can make this happen with geospatial data, it can happen anywhere. So the theme of this conference is shaping the future of AI. And that's where intelligent national maps can directly connect. They align with priorities every organization in this room probably has: trusted data, scalable automation, and explainability. We've heard a lot about all of those at this conference. If AI is going to shape the future of society, it can't work as a black box. It has to provide results that leaders can trust. And it has to be usable across systems. By understanding how to embed structure and validation into AI, we're shaping a future where AI earns trust instead of eroding it. We're not working on these problems alone, of course. There's lots of partnership opportunities here. Some I've listed, which include minimizing infrastructure requirements so that systems like ours are efficient and practical. Developing new agents and validation models are very much in need, especially surrounding the geospatial data arena. And then working on shared governance standards. So we have heard quite a bit of discussion about standards. Everything's still flying around. We've got to have these standards, and we need to have them be informed by a broad group of businesses. So looking forward, there's 3 areas of research that excite us, that we think are very important. One is foundation intelligence, that's shared AI that adapts across domains so that it can solve problems outside of its original domain. A second one is multi-agent systems that coordinate without micromanagement. And I've seen a lot of that here this week, these last 2 days. This makes the system more autonomous and resilient. And then the third is we need more spatial training data sets to increase the depth in the domain. So I'm going to close with a simple point. The future of AI must be trusted AI. That's what we're doing here with Intelligent National Maps by incorporating scientific validation. It's not just about the maps. It's about building AI that's explainable, trustworthy, credible, reproducible, to make real decisions about the real world. That's the future we can shape together. Thank you.
I think we have time for maybe a question or two.
Any questions?
Thanks for the presentation.
A little closer.
Thanks for the presentation. Real quick, are you guys focused more on the correctness of the geospatial data and also the time stamping of it, right? Because when you're talking about fast-moving scenarios like a wildfire, right, you want to understand spread risk versus, so you want to model things like ignition risk, spread risk. So do you do that kind of work, applied work? And you also want to compare it to how it actually spread. So you need repetitive satellite data of the same area or repetitive data, aerial data of the same area. So are you addressing these kind of issues?
Yeah, definitely. So USGS already addresses that, does that kind of research. The issue is making the results from that available more quickly, validating them more quickly, not going through a 3-month process to say, yeah, the data are perfect. So that's why validation is that issue that I bring up over and over again. How do we validate our gold stamp data and make it so that it's trustworthy and you can use it as an anchor? Good question.